Hello, this is Mr. Collier, and today we're doing area. Okay, we're doing area because we're going to relate that to integral calculus in a bit, but let's take a look at some just regular shapes today. So in real life, when you want to find the area of something odd like this island, you got to split it into shapes. Now you can probably try a couple of rectangles or something. You might get close, but the smaller you make it, the better. So one systematic way is to just split it into a bunch of small rectangles and add up those areas. Or if you want to get a little bit more accurate, sometimes it's useful to do a bunch of trapeziums or trapezia. Okay, so we're going to talk a bit more about that in a bit, but right now we're looking at the area of a trapezium first. Okay, the area of a trapezoid is in the form of the booklets, half a plus bh, where a, b are the parallel sides. So this is the a and the b in this case because these are the parallel sides. And that's the h. So you can see how to calculate the area here. This formula uses b1 and b2, but the formula of the book uses a and b. Okay, so for this area right here, we have half, and then we have 5 plus 7 times 3. And this is 12, so that's 6 times 3 is 18 square centimeters. Okay, so that's the formula for the area of a trapezium. Now we're going to be looking at some functions during calculus. So here's a function, and these are the parallel sides. So this is the height down here. It looks like it's 3. And we need to find the height, and we have a function, so you can just get the y value by substituting in 3.5, for instance. So that's negative 2 times 3.5 plus 8. That's negative 7 plus 8 is 1. So that's basically, that side length is 1. It's called A. And back here we can do f of 0.5. And we get 7. Okay, that's b equals 7, I guess we could say. So the area is half times 1 plus 7 times 3, which is half of 8 is 4, times 3 is 12. And this next shape, it's not a trapezium, but we can split it into 2 trapeziums. Okay, we need these points here. That we can substitute into this equation, f of 8, which equals negative 0.5 times 8 plus 7, and that is 3. We need this point. We can actually substitute into either of these equations to get that point. Oh, actually, we need to find the point of intersection first, and then sub in. Let's go get this point here first. That's just a y-intercept, so that's 3. Okay, so the point of intersection, we can do 1.15 plus 3 equals negative 0.5 x plus 7. You can solve by graphing, and sometimes that's the easiest way, but I'm just going to add 0.5x to both sides, so you get 2x plus 3 equals 7. 2x equals 4. X equals 2. So x equals 2. What's the y value? We can substitute into either equation. Should get the same thing. G of 2 equals 1.5 times 2 plus 3. That's 3 plus 3 is 6. Okay, and then you can get the area. The area equals, we're going to add 2 trapeziums together. So for this trapezium, this is 3 and 6, so that's 6 plus 3. The width is 2 because the x-coordinate there is 2. So that's all 9. I'll call that A1, and A2 is half, and this distance here is from 2 to 8, so that's actually the height, so that's 6. Sorry. Okay, so that is half of, this height here, this height is also 6, so it's 6 plus 3, and then you have another 6 here. So that's, actually, it's just 3. Oh, they're both 3, okay. So that's 9 times 3 is 27. Okay, so we add those together. The area is 9 plus 27 equals 36. Okay, next. Next, let's look at a velocity versus time graph. And let's check it out. So this describes the situation here. We can see it. It's going, the object is going 8 kilometers per hour. Now, if it's going 8 kilometers per hour, well, let's work that out in a second. Let's answer this question first. The graph is piecewise linear function. Determine the equation of the graph. Okay, well, we've got two different equations. We got here, like y equals 8, and here, this is y equals negative. The slope here is down 8, right 2, so that's negative 8 over 2, or negative 4. What distance, that's the important part, what distance did the object travel during the entire journey? So let's take a look at 8 kilometers per hour for 1 hour. That would be 8 kilometers, right? Or let's go to all the way to 4 hours. 8 kilometers per hour for 4 hours is 8 times 4, 32 kilometers. What we just did is 8 times 4. That's just the area of the rectangle. Okay, so the area underneath this velocity time graph is actually equal to the distance traveled. Okay, so that's why we're studying the area here. And then over here, we can do the same thing. The area is, well, it's a triangle, so it's half base times height. I guess I could have done a trapezoid for the whole thing, of course. This whole thing is a trapezoid, but I've split it into a rectangle and a triangle. Half of 8 times this distance is 2. So that's 4 times 2 is 8. So the total distance is simply 8 times, 32 plus 8. There's two things there, so that's 40 kilometers. Okay, and sometimes your velocity time graph looks something like this, and if you find the area under the curve, it also equals the total distance traveled, and we'll be doing that later with calculus and with something called the trapezium rule. Okay, yeah, which is what this picture is alluding to. Alright, so we have a couple more trapezoids here, which are easy to find the area of. Let's maybe just go over this one right here. Let's get the graph of the function negative 2x plus 6. Okay, so you want to get the area. It's just a triangle. We can easily find that, but let's just read this carefully. Shade the region enclosed by the graph, the vertical line x equals 0. There's the line x equals 0 and the x-axis. So we're talking about this triangle, and the area is, well, obviously simply half 6 times 3, so that's 3 times 3 is 9.